Welcome to the Deep Dive, where we distill essential sources into the knowledge you need. Today, we're taking a truly, insightful look at a critical journal article. It's called Perspectives on Genetic and Environmental Factors in Myopia, Its Prediction, and the Future Direction of Research. A really crucial topic for, anyone in ophthalmology, optometry, general eye care. It gives a great overview of where we stand with myopia.
That's right. And our mission today is really to synthesize these latest perspectives. We're looking at the driver's genetic, environmental exploring prediction methods and trying to peer into the future a bit. It's all about helping you get a clearer picture of this global health challenge and what it means for your practice.
Okay, let's unpack it. The article is by Katie M. Williams and Christopher J. Hammond, published in Investigative Ophthalmology and Visual Science. A fantastic resource, really brings the complexities into sharp focus. Oh, and before we dive deeper, just a quick note for you. There's a link to the full study we're discussing right there in the deep dive description, so you can check it out yourself after listening. All right, let's start big picture. The article says myopia has reached epidemic proportions over the last century. What does that actually look like?
Well, the scale is pretty staggering. We're seeing really alarming prevalence rates, especially in East and Southeast Asia. I mean, think about this. 50% of 9-year-olds in Singapore.
50%? Wow.
Yeah, and it gets higher. 95% of university students in Taiwan, over 96% of 19-year-old men in Seoul affected.
Those numbers are certainly eye-opening. Is it mostly an East Asian thing, or are we seeing it spread?
It's most dramatic there for sure, but no, it's not isolated. In the West, rates are climbing significantly too. Like nearly half of 25 to 29-year-olds in Europe are myopic now. And the rate basically doubled for those born in the 1960s compared to the 1920s.
Double.
And the big projection, by 2050, half the world's population could be myopic.
Half the world. That's a lot of spectacular patients coming our way. But it begs the question, right? If refractive error is supposed to be highly heritable, how do genes explain such a fast epidemic?
Exactly. That's the crux of the prevention paradox the authors talk about.
Yeah.
Evolution, genetic adaptation, that takes way longer. So genes alone just can't be the full story for this rapid rise. Which leads us to ask, okay, do we target the high-risk individuals? Or do we need a much broader population-wide approach?
Okay, so if it's not just genes, environment must be playing a huge role. The article fingers modern-day childhood, less time outdoors, more near work. What's the evidence on outdoor time?
That's a really key piece. The emphasis on outdoor activity is strong.
Yeah.
Early work, like the Sydney Myopia study, really highlighted it. It wasn't just about reducing the risk itself, but it seemed to buffer the effects of kids doing a lot of reading, too.
Interesting.
Yeah, and a meta-analysis confirmed it showed a highly significant reduced risk, like cutting the odds almost in half, even just based on parents reporting outdoor time. Animal models back it up, too, showing light levels matter, even seasonal changes in eye growth. Future work needs, objective measures, maybe looking at light spectrum, violet light, things like that.
So more sunshine, less myopia. What about the link with education? That comes up a lot.
It does, and it's a link that goes back centuries, actually. Education and myopia. The intensification of education systems, particularly in urban East Asia, seems like a big part of this modern epidemic.
Yeah.
And we have things like Mendelian randomization studies. Now, these use genetics to tease out cause and effect, and they do show a causal link between years of education and myopia risk.
The causal link.
Yeah.
Wow.
Yeah, though the exact mechanism, is it just the intense close work? Or is it simply because more school means less time playing outside? That's still a bit fuzzy.
Right. And what about reading itself, the classic suspect? Is the evidence strong?
It's often weaker than you might expect in general studies, often quite variable. But that Sydney Myopia study again, it found a stronger link when looking at intense near work. Things like reading really close, less than 30 centimeters, or reading continuously for over half an hour. Those things did independently up the odds. The WHO is apparently even working on a simpler diary to try and capture this better. So maybe it's not just reading, but how you read.
Which naturally leads to screens. Everyone blames screens. What's the real story there, according to the article?
Good question. And the evidence is still building. Older studies weren't clear-cut. But a more recent meta-analysis did suggest smartphone use, especially combined with computer use, is a significant risk factor. And there are longitudinal studies, like the Generation R study with 9-year-olds, that found screen time was an independent risk factor.
Okay, so maybe there's something to it.
Possibly. And look at the Ireland Eye study. 6-year-olds using screens over 3 hours a day had a 15.5% myopia rate. Compare that to just 3% for kids using them less than an hour. That's a big difference.
Huge difference. And then, bam, COVID lockdowns happened. The ultimate natural experiment, right?
Precisely. Lockdowns forced kids inside, and studies showed pretty significant jumps in myopia prevalence, especially in the younger ones, like 6 to 8 years old. And this went hand in hand with massive increases in reported screen time and, of course, less outdoor activity.
So, tying it together.
Well, the authors say the evidence isn't quite strong enough to pin it solely on screens, but they conclude it's probably wise to limit smartphone and tablet use in young kids. They even mention this really intriguing side note research suggesting black text on a white background might be more myopogenic, while white text on black could actually inhibit myopia progression.
Huh. That's a fascinating little detail. Okay, last environmental bit. Socioeconomic status and obesity. Historically, myopia was linked to higher SES, lower BMI. Is that changing?
It seems to be shifting, yes. A huge Israeli study from 2022, looking at over 1 million Army recruits, found this J-shaped curve for BMI and myopia risk. That's different from back in 1995. And recent studies from Korea and the Rotterdam Generation R study found kids from more disadvantaged backgrounds were actually more likely to be myopic now. The thinking is it might be linked to more sedentary indoor lifestyles, maybe tied to the rise in obesity too.
So it raises the question,
Yeah,
are these things, SES, obesity, screen time, truly independent risks? Or are they maybe just proxies for the big one, not
well,
getting enough time outdoors?
that's a great question. It does feel like modern childhood is kind of the umbrella term covering a lot of these interconnected factors.
Okay, let's switch gears. Let's put the genetic lens back on. Given that rapid environmental shift, how can genetics still be so important? It feels a bit counterintuitive.
It does, but it's a really crucial distinction to make. Family history. Still the strongest single predictor we see in epidemiological studies. And twin studies consistently show high heritability for refractive error, like around 80%. For spherical equivalent and axial length, it's about 71%.
80% is high.
It is. But here's the key. Heritability tells us about the proportion of variation within a population that's down to genes. It doesn't determine the population average. So you can have a trait that's highly heritable, but if the environment changes for everyone, like less outdoor time, the whole population average can still shift towards myopia.
Ah, okay. That clarifies it. The baseline shifts, even if individual differences are largely genetic. What about this missing heritability you mentioned in GWAS studies? What's that about?
Right, that's a puzzle in lots of common heritable diseases. Twin studies point to high heritability, but when we do these huge genome-wide association studies, GWAS, looking for common genetic variations, the SNPs, they only explain a fraction of that expected heritability. For myopia, maybe around 20%. Simulations suggest even with massive sample sizes, it might only hit 30%.
So where's the rest of the heritability hiding?
Good question. Could be rare mutations with bigger effects, maybe structural changes in DNA, epigenetic factors, things that change gene expression without changing the DNA code itself, or maybe complex interactions between genes, non-additive effects. Lots of possibilities.
Okay, so even with that missing piece, have we actually found any myopia
Oh
genes?
yes, absolutely. Progress has been huge there. Back in 2010, we really hadn't convincingly identified any. Fast forward to 2021, the biggest GWAs yet, by Hissy and colleagues, looked at over 500,000 Europeans. They found 449 spots in the genome loci linked to refractive error. Yeah, quite a jump. Now, each one has a tiny effect size on its own. But what's interesting is what they are. Many of these genes, when they have major mutations, cause known Mendelian eye diseases affecting almost all parts of the eye. There's a strong showing for retinal genes, which makes sense. The retina senses focus and drives eye growth. Others are linked to things like circadian rhythm, cognition, even intraocular pressure.
That's an impressive cornucopia of genetic insights. What about gene-environment interactions? You mentioned education interacting with some genes. Is that the key?
It's definitely considered one of the holy grails, trying to find how genes and environment interplay. But it's proven really tough, mostly because those individual gene variants have such small effects, it's hard to detect statistically significant interactions. We have found a few, like you mentioned, education interacting with variants, the GJD2 gene in Dutch people, or the ZMED4 gene and near work time. But getting these findings replicated consistently is hard. Plus, measuring the environment accurately, like outdoor time, is tricky too.
Right. So pulling this genetic thread together, what are the main implications for you, our listener, in your clinical work? Where might this lead?
Well, the big hope is that by understanding these genetic pathways, we might uncover new mechanisms that could lead to novel treatments. Think about how genetics revolutionized our understanding and treatment of age-related macular degeneration with the complement system insights. We also have tools like Mendelian randomization, MR now. Using genes as a sort of natural experiment, MR studies have shown education is causative for myopia, interestingly, not general intelligence, but years of education specifically. MR also showed that intraocular pressure, IOP, seems to be causative for both glaucoma and myopia, which is intriguing, right?
Yeah.
Maybe lowering IOP could become part of future myopia control strategies.
Interesting connection.
And then there's pharmacogenomics, using genetic info to predict who might respond best to certain treatments or who might be at risk for side effects. But we definitely need more large-scale studies, especially tracking kids over time and gathering more OS data, epigenetics, metabolomics, the works.
Okay, that leads perfectly into prediction. If we can figure out who's most at risk early on, we can intervene sooner. That seems critical.
Absolutely critical. The goal is personalized prevention, ideally while the eye's natural focusing processes in metropization are still really active. And consistently, the biggest single risk factor that pops up? Family history. Look at the Hong Kong Children's Eye Study. They found a really strong dose effect. If both parents were highly myopic, 56% more than half of their kids were already myopic by age 6 to 8.
56%, that's a huge signal. What other tools do eye care professionals have right now?
A classic, powerful one is cycloplegic refraction. We've known for decades that kids who are going to become myopic tend to be less hyperopic, less long-sighted early on. The benchmark study, the Orinda longitudinal study, found that having less than plus 0.75 diopters of hyperopia under cycloplegia at age 6 was the strongest predictor of developing myopia later. It gives a really good predictive signal, an AUROC of 0.88.
That's a great metric, though maybe a bit dilating for some kids to get. What about axial length growth charts? Are they becoming more common?
Yes, exactly. There's growing interest in using axial length growth charts, kind of like the height and weight charts pediatricians use. The Brand Holden Vision Institute, BHVI, has their myopia calculator, which includes normative axial length values, freely available online. These charts show important nuances. Axial length relates to height, so you need separate curves for boys and girls. And there are big differences between, say, European kids and Chinese kids. Using these helps spot kids in that pre-myopia stage earlier, and axial length itself is a better marker for the future risk of complications than just refractive error.
So tracking eye growth directly makes sense. How good is genetic prediction getting? You mentioned the GWS studies.
It's advancing. With the data from large GIs, we can now build polygenic risk scores, combining the small effects of many genes that HiAZ et al. Their score could predict low myopia with an area under the curve, or AUC, of 0.67, and high myopia with an AUC of 0.75. More recent scores, combining multiple GIs, have pushed the AUC for high myopia up to 0.78 in people of European ancestry. That's getting pretty good.
Decent prediction.
It is. But there's a major caveat. Most of these big GIs have been done mainly in European populations. When you try to use those scores in, say, African populations, the prediction accuracy drops off significantly. We desperately need more genetic data from diverse populations.
A crucial point for equity. Okay, what about artificial intelligence and machine learning? AI is everywhere else.
It's definitely making inroads here, too. Ophthalmic imaging, retinal photos, OCT scans generates tons of data, perfect for AI. One study used retinal photographs from the Singapore SCORM study. AI analysis of those photos could predict, with high accuracy, which kids would go on to develop high myopia later in their teens. And people are looking at AI measures from OCT scans too, things like choroidal thickness patterns, maybe even ocular volume, as potential future predictors.
So technology is definitely giving us a clearer vision for prediction.
For sure. And we're already seeing practical tools emerge, these data-driven myopia prediction calculators like the BHVI one I mentioned, commercial systems like Ocumetra, non-commercial apps like Primo. They're out there. The future really looks like integrating everything: demographics, refraction, biometry, especially axial length plus image analysis, maybe genetic scores, all fed into machine learning models for the best possible prediction.
Let's zoom in now on high myopia. The article calls it a neglected subgroup, a really concerning focal point. Why the special emphasis?
It really is crucial. Remember that prediction, 50% myopic by 2050? Well, the estimate is at least 10% of those will be highly myopic. We're talking -6 diopters or worse. And that's deeply concerning because high myopia isn't just about needing strong glasses. It exponentially increases the risk of serious sight-threatening conditions later in life. Things like myopic maculopathy, retinal detachment, glaucoma. One study estimated 1 in 3 people with high myopia will end up severely visually impaired by age 85.
1 in 3.
And if your prescription is really high, say MAGA 12D or more, your lifetime risk of visual impairment jumps to over 90%. It's a major, major public health issue hiding within the larger myopia epidemic.
A long-sighted problem with serious consequences. What makes high myopia distinct, especially when it starts early?
A key factor is the young age of onset. If a child becomes myopic very early, the International Myopia Institute uses a rule of thumb like myopia in diopters greater than the child's age in years. It often signals a stronger underlying genetic cause. We can think of two broad types. There's the common, high myopia, likely resulting from many small effect common gene variants plus environmental triggers. And then there's Mendelian or syndromic myopia, caused by a single, high-impact pathogenic gene variant. These often come with other systemic features. Think connective tissue disorders like Stickler syndrome or certain retinal dystrophies. Researchers have identified specific genes for some isolated early-onset high myopia cases too, like AR3, which has this unusual X-linked pattern where females are mainly affected, and KDLR3.
So for these kids with potentially Mendelian forms or just very early onset high myopia, what about treatment? Are standard myopia control methods effective?
That's a really important question, and honestly, the evidence base is thin. Historically, these highly myopic kids were often excluded from the big myopia-controlled clinical trials. We have some small case series that offer hints. One looked at 14 kids with confirmed Mendelian myopia. High-dose atropine, 0.5% or 1%, seemed to slow their axial length progression by about 27%. There was also a report on red light therapy in China in 3 kids with Stickler syndrome. It apparently shortened axial length in 5 out of 6 eyes.
Interesting anecdotes, but
Exactly. Anecdotes. The article is very clear on this. Right now, myopia-controlled treatments for diagnosed Mendelian myopia do not have a solid evidence base. They should not be actively recommended without considerable caution and discussion with the family. We really need more rigorous studies in these specific high-risk groups.
understood. Okay, so given the scale of this whole thing, public health interventions seem vital. What's actually working on that front?
The big success story seems to be interventions focused on increasing outdoor time for kids at a population level. Taiwan's Tiantian 120 program, started back in 2010, aimed for 120 minutes of outdoor time per day in schools. It actually managed to stabilize the rising myopia prevalence in elementary kids. It went from 50% down to 46%.
Stabilize it. That's impressive.
Even more so was their Yilan Myopia Prevention Program, YMVIP, for preschoolers. Prevalence dropped from over 15% down to around 8.5–10%, and it stayed down, even during the COVID disruptions.
That's a real win for getting kids outside.
Absolutely. And in China, the GYL study was a proper randomized controlled trial. They added an extra 40-minute outdoor lesson daily. Over 3 years, the incidence of new myopia cases dropped from 40% in the control group to 30% in the outdoor group. Now, the effect on slowing progression in kids who are already myopic was generally less pronounced in these population studies, but as a primary prevention strategy, getting kids outside seems key.
We keep coming back to the outdoors. You mentioned the COVID-19 lockdowns again. What did they really underscore about interventions or lack thereof?
They basically showed us, in stark terms, how quickly things can change with environment. Those Chinese studies tracking hundreds of thousands of kids, seeing prevalence jump from 53% to 59% in just 1 year between 2019 and 2020, especially in the younger kids.
Wow.
And the Hong Kong Children's Eye Study directly measured significant increases in refractive error and axial elongation after a severe lockdown. It just hammered home the impact of being stuck indoors, likely more screen time, definitely less outdoor time. It showed how potent those environmental factors are.
Okay, so outdoor time is a public health win. What about pharmacological prevention, like using atropine not just to slow progression, but to prevent onset in at-risk kids?
That's definitely being explored, given how well low-dose atropine works for slowing progression. The LMP2 trial in Hong Kong specifically tested this. They randomized pre-myopic kids to 0.05% atropine or placebo. Over 2 years, the incidence of myopia was cut almost in half. 53% in the placebo group became myopic versus only 28.4% in the atropine group.
That sounds promising.
It does. A similar study in Japan using 0.01% atropine also found a significant difference. But 2 big caveats. One, most of this prevention data is from Asian populations. We need to see if it holds elsewhere. And 2, there are significant regulatory hurdles to overcome before you can routinely prescribe a drug prophylactically like that, especially for kids. It brings us back to that prevention paradox again, doesn't it? Population approach versus high risk. Atropine prevention feels more like a high-risk strategy.
Makes sense. Let's talk about technology for monitoring. What advancements are helping or what's needed?
Well, regular, accurate measurement of refractive error is still fundamental. But yeah, tech can help. The article mentions the The dream of a non-stinging cycloplegic eye drop, or maybe an autorefractor so accurate you just don't need cycloplegia at all, that would certainly make clinic life easier.
Oh, a true vision for pediatric eye care.
Wouldn't it be? But more realistically, axial length growth curves are becoming critical. Why? Because minimizing how much the eye grows in childhood is really the only way we can reduce that final adult axial length and cut the risk of those long-term complications. Remember, slowing myopia progression by just 1 diopter can potentially reduce the likelihood of myopic maculopathy by 40%. That's huge.
40% reduction,
And
okay.
tracking axial length lets you see progression more directly than just refraction. Elongation rates differ. Asian kids tend to elongate faster, about 28% more than non-Asians in meta-analyses. In the UK, fast progression is often defined as 0.58D or more per year. While the devices aren't everywhere yet, biometers are getting more accessible. They're highly sensitive, accurate, quick, non-contact, a really vital tool for precise monitoring, especially if you're intervening.
And what about advanced imaging? Retinal photos, OCT.
Yeah, they play a big role too, especially for monitoring the consequences of high myopia. Retinal photography, combined with grading systems like the Meta-PM system, helps track myopic maculopathy changes over time. Studies show over 40% of high myopes show progression in these changes over about 13 years. And deep learning applied to fundus photos, as we mentioned, might predict future high myopia risk. OCT scanning is also powerful. It lets you see the choroid, that layer under the retina. It seems to be quite dynamic, responding to defocus even before the eye starts growing longer. Choroidal thickness actually increases with low-dose atropine and with outdoor time.
Interesting. A potential biomarker.
Potentially, yeah. OCT can also image the shape of the back of the eye, looking for staphylomas, those outward bulges common in high myopia. How exactly staphylomas influence risk and progression is still being worked out, but imaging them is getting better.
So lots of insight from imaging. What about measuring those tricky environmental factors? Light, reading, screen time, any tech helping there?
That's still a challenge. We need better wearable light meters. Current ones can be blocked by clothes, or kids just don't wear them long enough. Spectacle-mounted devices like the ClueClip are an improvement, but obviously only work if the child wears glasses. For reading and screen use, which have been really poorly measured historically, we're starting to see objective tools. Apps like the Myopia app, devices like Range Life that can track smartphone use, face-to-screen distance, viewing distance, the ideal. Probably some kind of small, wearable sensor, not tied to glasses, that works all day and integrates light sensing with activity or near-work tracking. We're not quite there yet.
Okay, one last area the article touches on that might surprise some listeners. Myopia progression in adulthood. We tend to think of it as ending in the teens.
That's a common misconception, but yet definitely continues for some. While most myopia starts in childhood, maybe up to a third of myopia cases in Western populations could actually be adult onset. We see higher rates in certain jobs involving intense near work. Like clinical microscopists, one study found 33% develop myopia after age 20. Now, these adult-onset myopes don't usually develop the really severe pathological changes, but because there are so many of them, they still add significantly to the population risk for things like glaucoma, cataract, and retinal detachment. It's not just a childhood blur.
So progression doesn't just stop at 18. We need to keep an eye on adult patients too.
Absolutely. Progression definitely occurs in early adulthood, especially if risk factors continue, like going on to university. Studies show an average progression of maybe 181D between ages 20 and 30 in university groups. Even outside university settings, a Finnish study found adults in their early 20s progressed, on average, just under -0.5D over 8 years. And while the average yearly progression slows down a lot by age 30, maybe only get at 0.1D per year, population data clearly shows the proportion of high myopes keeps increasing with age. This suggests that even slow adult progression adds up over time and contributes significantly to the overall burden of pathological high myopia.
Wow, what a comprehensive deep dive this has been. We've covered the global epidemic, that complex dance between genes and environment, cutting-edge prediction tools, the crucial focus on high myopia, and even adult progression. So much to optic about.
Indeed. I think to summarize, the article makes a strong case that this myopia epidemic is really a consequence of our modern childhood lifestyles. Less time outdoors seems key, probably more intense near work, maybe screen use playing a role, even shifting socioeconomic factors.
Yeah.
And while individual susceptibility is highly heritable, the sheer scale of the shift means population-level interventions, like promoting outdoor time, seem really critical.
Right. And on the clinical side, things like axial length growth charts, maybe polygenic risk scores down the line, AI helping with prediction, these hold real promise for more personalized intervention. But the research also clearly highlights where we need more work, especially understanding and treating those kids with very early or Mendelian high myopia and getting a better handle on adult progression.
Exactly. The big challenge now is translating all this rapidly evolving knowledge into effective strategies, both in our clinics and for public health policy.
Absolutely. Before we wrap up, if you, our listener, found this deep dive valuable, please do consider following the deep dive on your favorite podcast platform. That way you won't miss future episodes. And hey, if you really like this content, if it was helpful for your thinking or your practice, leaving us a 5-star rating genuinely helps us reach more people like you. We'd really appreciate it. So, the final thought to leave you with. Considering these rapid advancements in prediction, the ongoing rise in prevalence, and the tools becoming available, what changes might you prioritize in your own practice to better manage and hopefully prevent myopia in your patients?
We certainly hope this deep dive helps you see things more clearly in this constantly evolving landscape of myopia.
Until next time, keep exploring, keep learning, and keep asking those deep questions.